Alright, this is going to be the lecture video for Chapter 8, Potential Energy and Conservation of Energy. So, main topics for Chapter 8 are determining what's a conservative and a non-conservative force, potential energy and the work done by conservative forces, conservation of overall mechanical energy, work done by non-conservative forces, and potential energy curves and equipotentials on graphs. So, conservative and non-conservative forces. Anything that is conservative force, that means the work that the object does is stored in the form of energy that can be released as kinetic energy at a later time. For example, gravity. A non-conservative force is where it can't release kinetic energy. Things like friction. Friction cannot be released by kinetic energy. It just doesn't work like that. So the work done by a conservative force that moves an object is on a closed path. That's also a big difference. If your object is in a closed path, it goes from A to B, it stays in the frame of reference, and these are conservative forces acting on it. If you have a non-conservative force, it doesn't have a closed path. It's kind of like an open system in a way. So the work done by gravity on a closed path is 0. That means if you started with your box up here, you would have your force of gravity. You move it to the left and down. Now the work being done is potential energy. You would have no work done up here. When it goes back on the bottom side, the work is 0 because you're going at that right angle. If you're going back up a certain height, then your work is equal to negative potential energy. So when you take the sum of your works, they would equal 0. The vertical work done and the horizontal work done are both equal in opposite direction. Friction is not 0. The work done by friction on a closed path is not equal to 0. If you take your box, the work done is equal to coefficient of kinetic friction times the mass, gravity, and displacement. Going around to the left, you have negative coefficient mgd. Down at the bottom, you still have negative coefficient mgd, and so forth on the right side. So if you took the work done and put them all together, you would not get 0. So the net work done on an object in a closed path is 0 for conservative forces and not 0 for non-conservative forces. The work done by a conservative force is independent of the path. Doesn't matter which way it goes. The work done to go from point A to B is work 1. Right, so if you go from A, follow the pink line to B, the work done from B to A is negative work 1, and it's independent of the path. Like you could go different ways to get from B to A, and the work is going to be independent of each other. It doesn't have to follow a certain path, basically. Alright, so more on the work done. We know for work that it is dependent on the direction of your force and your displacement. So if both force and displacement are run parallel with each other, right, they're both vertical or they're both horizontal, then work is done. If they are not, if they are perpendicular with each other, so force is horizontal and displacement is vertical, then you have no work being done. So if you pick up a ball and put it on a shelf vertically, you have done work. You can get that energy back if the ball falls back to where it started. This stored energy is called potential energy. The object has the potential to be moved. So potential energy is when an object is typically not moving, it just has stored energy. So we represent potential energy by capital U. So you can say the work done by conservative forces is equal to initial potential minus final potential, or rearrange it, right? Change the signs. Then you have the negative change in potential energy. Just like kinetic energy and work, potential energy is measured in joules. So for gravitational potential energy, you can say that this is equal to the mass of the object times the gravity times the height that it goes. So gravitational potential energy is reliant on gravity, hence the name. So that's why gravity is in your equation. So if you measured the potential energy from point A to point B, you have some sort of height. All right, so we'll call this y1. From A to B, you have gravitational potential energy. If you go from B to C, you don't have gravitational potential energy. There is no y. There is no change in height. So there is not gravitational potential energy. If you go from C to D or C to E, you still have a change in height. It's just going to be negative, which is perfectly fine. And if you go from D to A, you have gravitational potential energy. Same thing if you go from A to E, E to A, D to E. As long as there's a change in height, you have gravitational potential energy. And then springs. So we kind of looked at this equation before. This is what's called elastic potential energy. Sometimes you'll see it as UE. And it's 1/2 times the spring constant times the displacement of the spring from its equilibrium point. So not just how far it stretches from the wall to the hand. That's not x. X is how far from equilibrium to wherever it stretches. So make sure you keep that in mind. Mechanical energy. Mechanical energy is just a fancy way of adding your potential and kinetic energy together. So you represent mechanical energy as capital E. Mechanical energy is always conserved. The amount of potential added to the kinetic energy is going to be the same as when you start as when you end. All right, you can transform energy as heat, sound, and it is technically lost, but it just gets dispersed. That doesn't count as mechanical energy though. Only potential and kinetic energy count. So you can always say that mechanical energy is conserved. Other types, not so much. So energy is another way of solving some kinematic problems. So those types of problems we saw in the first unit, you can use energy to find the same exact thing. So if you know that potential energy initial is mass times gravity times height, because it's not a spring, it's not stretchy, so it's not elastic potential energy. You know that if you're holding them above a certain height, then you have potential energy. Since it's not moving, you don't have kinetic energy. When it falls to the ground, when it hits the ground, it doesn't have a height, so the final potential energy is 0. But it has all kinetic energy because it's in motion. So if you were to write out, so Ui plus Ki, right, initial mechanical energy is equal to final mechanical energy. So in A, you don't have initial kinetic energy, so that's just 0. You don't have final potential energy, so that's 0. So you can say mass times gravity times height initial is equal to the final kinetic energy of the keys. And since mass is on both sides, they cancel. So then you have g times initial height is equal to 1/2 times vf squared. You can rearrange to find velocity. So if you multiply by 2 on both sides, right, get rid of that fraction. Then to get rid of the squared, just take the square root. So you can say final velocity of the keys in this case, square root of 2 times gravity times the initial height. All right, this also goes for springs. All right, you can say initial potential energy is initial mechanical energy is equal to initial potential energy plus initial kinetic energy. So you would just plug in the formula, right, to figure out whichever energy that you need. All right, so work done by non-conservative forces. The total work done is equal to the work done by the conservative forces and the non-conservative forces added together. Since we know the conservative forces work is equal to negative potential energy, you can replace that in the equation, adding the non-conservative work, and that's equal to your kinetic energy. So you rearrange, right, add the change in potential energy, then you would get non-conservative work done is equal to change in potential energy plus change in kinetic energy, which is your overall change in mechanical energy as well. It's another way of rewriting it to help you figure out non-conservative work done. So in this example, the non-conservative force is the resistance force of the snow, aka kind of like friction. It's preventing it from moving. All right, then we talk about roller coasters. Roller coasters are probably one of the easiest examples to do with energy, because essentially you can plot gravitational potential energy by looking at a picture of a roller coaster. When you go to Six Flags or SeaWorld and you look at the roller coaster, you're looking at its height. All right, in real time, you're looking at the height. So you can say, all right, here's the tracked little roller coaster. At point A, the ball or the roller coaster cart hasn't moved yet, so you have all potential energy, no kinetic energy. As it goes down to B, you are losing potential energy, right? You're decreasing height, so you're decreasing U, but you're gaining kinetic energy because you were getting faster as you were going down. When it goes back up over the hill, right, you're slowing down, so you have less kinetic energy, gaining more potential energy because your height's increasing, specifically here. All while this is happening, the total energy doesn't change. U plus K is always going to be equal to that initial total mechanical energy. It's just going to fluctuate depending on the point in the roller coaster. Graphing it for a spring is a little bit different. Kind of looks like a parabola. Makes sense, right? 1/2 times K times X squared. X squared gives you a parabola. So if you have your equilibrium point here at 0, and then you have X as negative A, and A just stands for amplitude, and so the height of your graph, and then to the right, how far it stretches, the maximum is positive amplitude. So total mechanical energy, right, is in that sweet spot in the middle. When you have the turning point, right, this is the maximum over here. This is as far as it stretches or compresses. After it passes here, then it goes back towards positive, and as it goes through equilibrium, so the 0, it has the maximum kinetic energy and no potential energy. All kinetic, no potential. As it gets closer to amplitude on both ends of the spectrum, you have max potential energy and no kinetic energy. Because at these points, your box isn't moving for that millisecond. It's just staying still. So you see the fluctuation in the parabola. And if you keep graphing, then it's going to look like sine and cosine graphs, which we'll talk about that when we do harmonic motion in a couple of chapters more in depth. More real-life examples. Contour maps. They are also a form of a potential energy curve. So if you've never seen one before, it helps measure elevation. So the contour lines are spaced closely if your elevation is close to each other. So if you only go from 100 to 150 meters, those lines between are going to be close. Versus if you go from the 100 line to 400, you have more space in between, which shows a greater change in height. But this also represents gravitational potential energy, because you're just talking about heights, right? And it's just mass times gravity times height. The only factor that changes is the height.